Hey everyone, how's it going? Welcome back to the class. If my voice starts to go during this lecture, it's because I spent like 3 hours recording stuff yesterday for other content, and so I've been talking so much. Hopefully it's alright. How are the volume levels out there? I just like to check that every time. Perfect. Okay, so I've always wanted to try this, and while I have my window open, let's see what happens when I do this. Nice. That's amazing. There we go. My experiments, my hypothesis was correct. What would happen if I did that? I don't think we could have the whole lecture like that, though. That may get a little strange. All right. So last time we introduced assignment 2, and turns out that I forgot to look over the code. I gave an hour-and-a-half long lecture on just like what the assignment was, but I didn't actually open up the assignment and go through the code. So what's going to happen is I'm going to give today's lecture, and then for about maybe 10 or 15 minutes at the end of the lecture, I'm going to go back through the code of assignment 2, because I didn't actually do that from the last assignment, or for the last lecture. And assignment 1 is due. I can't remember how many, pretty much everyone submitted it, so that's good. Our markers are going to have a little bit of work ahead of them. There's a lot of people in the course. But today's lecture is on the topic of hash functions and hash tables. The next lecture, so next week's 2 lectures are going to be on a little bit of game theory. And if you can attend those lectures live, it would be awesome, because we're actually going to be playing a couple of games, which will be really fun. I'll be sending out like a Google form to answer questions in the middle of the class, and we'll see how the results of those games go. Oh, excuse me. What's up with the weather here in Newfoundland the past couple of days? It has no business being like 22 degrees at the beginning of October. But anyway, let's get started with this stuff. Where is my PowerPoint scene? There we go. Okay, so as I said, at the end of this lecture, we'll be talking about some assignment 2 stuff, but not for very long, just going over the code. And today's lecture is on hash functions, hash tables, why they're useful, where we would want to use them, how we can use them in assignment 2 or even assignment 3 if we want to, etc., etc. So first of all, what is a hash function? I'm sure that some of you out there have used hash functions before, but we're going to go in detail about what they are. There are some really complicated hash functions out there. We're not going to be talking about too many of those specifically. We're just going to be talking about like some basic ones, so you get the idea, and then later you could go look at more complex ones and know what they're used for. So a hash function is a function which is used to map data of an arbitrary size to data of a fixed size. So for example, let me get my laser pointer out here. Let's say that we had a name which was given as a string. Okay, so we have some data which is a string representing something like a name, and we wanted to turn that into, say, an integer for some reason. Well, we can use a hash function to turn pretty much any data in any format into data of another format. And usually, the input size is of a variable size, and the output size is of a fixed size. Values returned by hash functions are called hash values, hash sums, or hashes, okay? So depending on where you go, you might see, oh, the output of this is called a hash value, or it's called a hash sum, or a hash. Hash values are commonly used as indices into a lookup table or a hash table. So lookup tables can be used in many different contexts, but if we're applying a hash to some data and we get an indice that we can look up in a table, then we're going to call that thing a hash table. So just as an example of some hashing here, let's say we have the input value of a string. We're going to pass it through some hash function, and the hash sum or hash value that we get is going to be a fixed length integer value. So for example here, we see that we're passing in fox. It goes through some hash function, whatever that may be. And then as an output here, we get a hash sum. Here we're listing it in hexadecimal, but it's just an integer value. And we can see here that when we pass in a different string of a different length into the same hash function, we get a completely different hash sum out. And we'll talk about how hash sum values differ in a slide or two. And here, when we pass in another hash function or another string, even though it only differs by one word, this particular hash function, whatever it is, will produce a completely different value for the hash sum. So what are some uses for hash functions? Why would we actually want to use one of these things in practice? One good use, as I kind of alluded to, is a hash table. So what we can do is we can use a hash table to quickly find data by computing an index or a key from some data, that's the input to a hash function, and then the index into the hash table would be the output of the hash function. We can also use hash functions for data protection. So for example, if we were creating a website and we didn't want to store our passwords in plain text, we could instead store the password hashes so that the original password can't be retrieved. So the way this would work is that in your database somewhere, when someone creates an account, you don't store their actual password, you store a hash of their password. So for example here, if their password was fox, you wouldn't store fox in plain text, you would store this hashed value. And then when the user goes to log in and they type in a new password, not a new password, but they type in their password, instead of comparing the thing that they typed in right? You hash it first, and then you compare the hash of what they typed in to the hash of what was stored. We could also use it for data verification. So, for example, let's say we have some data that might be gigabytes in size. And if I want to send you that data online and somehow verify that the data I sent you is actually the correct data, so for example, the data that I have is the data that you actually received, then what we can do is the following. We could apply a hash function to that really large data, and we can obtain a smaller integer value, which we call a checksum. And then that checksum can be verified later. So for example, I might have data which is a couple of gigabytes. I will run a hash function over that data, and it'll produce a checksum value. Then when you download the data, you can run the same hash function over that data, and if you get the same checksum that I got, then you can be pretty sure that the data that I have that you were trying to download is the data that you actually obtained. And so on some websites, if you've ever seen like a large download be accompanied by a checksum, that's why that will happen. Also, we could use geometric hashing. So geometric hashing is used in many proximity-based problems or algorithms in computational geometry. And in that, what we would want to do is maybe take some data which is in a much higher dimensionality and maybe reduce it to a smaller dimensionality. So when it comes to container membership query in assignment 2, we could use hashing and maybe a hash table to do something like store the closed list. So the open and closed list membership is one of the most common used queries in our search functionality, in our search algorithms that we're doing for assignment 2. So how you store the open or closed list matters for membership query. So for example, if you store the open and closed list just as a list or as an array, then in order to look through that list to see, for example, is this thing in the closed list, then you're going to have to look through that entire array. So you'll iterate through each member of the array, and in that iteration you'll say, is this thing equal to the thing that I'm looking up? And if you do that, then of course you know from your algorithms course that this is an O of n membership query. So this is a linear scan of the array in order to find something. If instead we use a set or a dictionary, maybe what we do is we get down to O of log n time from O of n time. If we use a hash table, then we can get membership query down to O of 1 in the best case, but as we'll see later, in the worst case, it will be O of n. But if we have something called a perfect hash table, which we'll look at later again, then what we could do is we could change the membership query of something like the closed list from O of n down to O of 1. So we would be able to tell, is this thing in the closed list, or maybe even if this thing is in the open list, in constant time. And I think I actually talked about how you could do that specifically in assignment 2, but we'll see after this lecture, you'll know how to do that for sure. So then, what exactly is a hash table? So to hash a data structure means to represent it in another form. And that other form is going to be a fixed form or a simpler form, typically. So typically, hashing is done by a function that turns a data structure, as I said before, like a string or some other data, into a number. And the numbers that we use are important as the output. Typically, we're going to prefer using integers for several reasons. First, computers store and handle integers efficiently, so whenever we can do things using integers, we want to. They can be manipulated efficiently, so integer arithmetic is really, really quick. And so if we want to do things like bit shifting or additions or multiplies on integer, those are faster than, say, using floating point numbers or doubles, etc. And not only that, but maybe the most important thing is that integers can be used to index into an array. So if we compute an integer hash, then we can think about looking up that integer as the index into an array. And if we do that, then what we have is a hash table. So what are the inputs into our hash function? The hash function is going to be a very specific function, and it might be hand-coded, it might be a neural network, it might be something completely custom, and so that function, just like any other function, is going to expect data in a given format. Hash functions might also expect a given range of values from a particular input format. So for example, some hash functions may say, well, I'm only going to be accepting integers in the range of 0 to 1,000,000. Or they may also say, I'm only going to accept strings that are of at most length 32, or something like that. Hashing an unexpected input value or a value from outside the range may produce poor or undefined results. So again, our hash function is going to expect very specific input or a very specific range of input, and then produce output in a very specific format. So if we break those formats, just like any other function, that may not work out for us. What about the output of a hash function? Well, a hash function is always going to produce values in a predefined format and range. So for example, we're going to produce an integer which is between 0 and 1,000,000. That's if we have, say, a 1,000,000 length array, then our hash function might be producing values between 1 and 1,000,000. The range is very important for the output of a hash function because it's often used as the index for a lookup table or an array, right? So if we have a table of a given size, then we may want to fix our output size based on that hash table size. And integers are also convenient here because we can use the Modulus operator to control the output range. And I'm going to show an example of that later. So some properties of hash functions. First, and maybe most importantly, is determinism. So a good hash function should not be random, so that it always produces the same value for any given input. So think about this. Remember the checksum I was talking about earlier? So imagine if a checksum function wasn't deterministic, if it had randomness in it. So I hash my big data into a checksum, and it has some randomness. So I get a number, and then I send you the data, and you run the hash function over the same data and get a different number. That would be brutal. So I can't think of any situations where you would actually want your hash function to have randomness in it. So determinism is a really important property for hash functions. Also, uniformity. So a good hash function maps inputs as evenly as possible over its output range, which helps to prevent expensive hash collisions. So what I mean by this, and we'll talk about what hash collisions are in a bit, but let me just come over to the blackboard here. All right. So what I mean by uniformity is something like the following. So let's say we have a predefined output range, right? So this may be like 0, 1, 2, 3, 4, 5, all the way up to some value n over here. And so our hash function, let's say we have our hash of some input, and then the output of the hash function is going to take these values, trying to find my brush here, and it's going to put them somewhere into this range, right? So one value may go here, one value may go here, one value may go here. And what we want to see is that if we hash a bunch of values, we don't want like a bunch of them clustering up in the center or a bunch of them clustering up here. If we input a bunch of different values, we want it to be spread sort of evenly over the whole range of values. Now, there might be really weird edge cases where you don't want that to happen, but in general, we want uniformity in our hash functions. Okay, let's go back to our PowerPoint. The output range. So it is desirable to have a defined range for the hash output as well as a fixed width. Okay, so usually what this means is that we're going to pick, and this is like 99% of cases where we produce an integer output, is that we're going to pick a range of integers for our output, usually between 0 and some number. Also, we may want data normalization. So what that means is sometimes our input data is going to contain features that are irrelevant, right? Maybe we have upper or lowercase letters. So if I'm hashing names, and those names are going to go into like a phone book, and I want to use a hash table to represent the phone book, well, I don't want the fact that one person may have typed their name with all uppercase letters, one person may have typed it with all lowercase letters, or some people may have like just capitalized the first letter of their name. I may want to just discard all of that irrelevant information, right? I want to put a name into this hash table. And so some of our hash functions may do data normalization where they take those unnecessary details and just throw them out during the hashing process. Continuity is also something very important. So, do small changes in input values have small changes in output values? Sometimes we may desire that, right? And sometimes we may not desire that. So, for example, maybe in some geometric application, we would want a small change in the input value to result in a small change in the output value. But in some areas like cryptography, we may want small changes in the input to have huge changes in the output. So let me just go back to the blackboard again real quick. I want to show you an example of that. So here we are at the blackboard. So let's say we have a problem in geometric hashing, for example. So in geometric hashing, let's say we have some space, and that space might be two-dimensional, it might be three-dimensional, and let's say my whole point here is that I'm trying to map a point in this n-dimensional space into a point in this one-dimensional space, which is the output of my hash function, right? So if I have some three-dimensional space here, just three-dimensional for example, and I have a point living in this three-dimensional space, let's say it's at this point here, right? Then I want this value to be hashed somewhere into our output range. Now, maybe the algorithm that I'm using here, if I have another point that is really, really close in this three-dimensional space, then when I hash this value, I may want it to actually be very close in the output space of the hash function. And again, this line is our hash. And the reason for this maybe is because if I'm, say, iterating over the values of my geometric space, then I want to also be iterating over similar values in my hash output range for things like cache coherency or whatever. But another example where I don't want this to happen might be in, say, cryptography. So let's say I'm doing the hashing of passwords. So if I have a password which is like password 1, right? And I have a password which is password 2, then I don't want those. I want these to be as far away from each other as possible when they get hashed. And the reason for that is that maybe if someone figures out the hash output value for one password, then if I had a very similar password on my next try, then they may be able to guess the hashed value of this password or get back to the password from the hash value if they are very similar once they're hashed, okay? So there are most cryptographic uses of hash functions, we would want the output to be very, very different, even if there's only like one character change in the input value. All right. Oops. Reversibility. This is a good one. So some hash functions can be invertible. And what that means is that we could obtain the input back from a given output. So again, this might be desired. So for example, in those geometric applications that I showed, maybe if we have a hash sum, we would want to be able to extract the point in 3D space that was used to hash this. Or maybe not, certainly not in the case of cryptography or password hashes, right? So if someone broke into our database and they found all the hashes of the passwords, we certainly wouldn't want them to be able to get back to the password from the hash value. And the reason for that is because, they would have complete access to our system. And so non-invertible hash functions are also called one-way hash functions. And in some cases, we would want them to be invertible, and some cases we wouldn't want them to be. So someone in the chat has a question. Why are some invertible and some not? Well, we'll talk about that, okay? That's going to be coming up on in future slides. Okay. So hash function algorithms, right? We've been talking about hash functions, but so far they've just been these magical things that just exist. So first off, we have a trivial hash function. So a trivial hash function is when the data for the input is already represented somehow by an integer, okay? So this is when typically very small amounts of input data range can be directly translated into its integer hashed value. So for example, an ASCII character can be mapped directly to an integer just by taking its own integer value. So again, an ASCII value is text was represented in the ASCII character set by a number between 0 and 255. And when you display that on the screen, it looks up in this ASCII hash table map what the character should be and then displays it on your screen. So that's an example where the data is already represented as an integer, and so hashing it to an integer is trivial. We also have a concept of a perfect hash function. So, and I'll talk about injective and surjective and bijective in a minute, but an injective function is one where each possible input maps uniquely to a value in the output range. This is also called a one-to-one function. And so perfect hash functions will be one-to-one and onto, or bijective, and I'll talk about that in a second. So we can have properties of hash functions as well, and these are actually theoretically very, very important and very, very good as an exam question, wink, wink. So I may give you an example on the exam of a hash function, and you would tell me whether or not it's injective, surjective, or bijective, and why, etc., etc. So in an injective function, each input maps uniquely to an output. So this means, so some output values may still be unmapped, but each input possibility uniquely maps to an output. And injective functions can be made invertible, and I'll show a diagram of this later, why that is, and why that's intuitive. A surjective function means that for every output value y, there is at least one input value x such that f of x equals y. And by definition, and we'll see this in a slide or two, surjective functions cannot be inverted. And the reason is, well, I'll show you that in a sec. In bijective functions, the inputs and outputs map uniquely. So that means that the input range of possibilities is the same as the output range of possibilities, and each one of the inputs maps uniquely to an output. So from mathematics, you may have heard this as one-to-one and onto, right? Injective is one-to-one, this is onto. And we can call this as well a minimal perfect hash function. Okay. So if we look over here, and you may have done this in math in high school, this function here passes the test of injectiveness. Why? Because each value of x maps uniquely to a value of y. This one fails the injective test because there are multiple values of x, for example, this value of x and this value of x map to the same value of y. Okay? So if two different values of x map to the same value of y, then it's no longer injective. Over here, we can see an example maybe of our hash table where we are hashing names into integers. Over here, we see that the name of John Smith and Sandra D both mapped to the same integer value. And so if we have two inputs, right, this is just like our x values over here on the left-hand side. So the John Smith and Sandra D are both our input values. And if they both map to the same output value, which they do in this case, then this hash function is no longer injective. So let's look at some of these properties. And yes, I stole this from Wikipedia. So this function here is injective, but not surjective. So why is it injective? Because each of the input values of x uniquely map to a y value. Okay? But it's not surjective because there's a y value that does not have an x value. All right. This one is an injective and surjective function because each x value maps uniquely to a y value, and each y value has an x value which maps to it. This one is or the one on the third one here is a non-injective function, but it is surjective. It's not injective because two x values give us the same y value, but it is surjective because all the y values have an x value which map to it. And this one is a non-injective, non-surjective function. The reason it's not injective because two x values map to a y, and it's not surjective because one of the y values doesn't have an x that maps into it. Now, let me just clear these. I'm going to clear these annotations real quick and come back. So, let's look intuitively then why an injective function could be reversible. So, over here we have an injective function, right? So, an injective function could be reversible because all of our input values map uniquely into an output value. So if that's the case, then there could be a function on the output value which maps uniquely back to the input value. But if we have a case of a surjective function, right, that is not injective, so here we have this case, so this is surjective but not injective. In a surjective function, we could still have the case where multiple input values map to the same output. So this can't be reversed. Why? Because if we have, say, the value of 3, which maps to a value of C in the output range, and also a value of 4 in the input, which maps to a value of C in the output range, if we try to reverse the hash function, well, which of 3 or 4 do we output? Right? We don't know which one it is. So we could write a function that reverses it, but it wouldn't give us the unique value that produced it. And so if we can't get back to the unique value that produced this, then it's no longer reversible. The best case possible of reversibility is a bijection, right? Where we have each value in the input range mapping uniquely to a value in the output range. Here you can think of, for example, where I talked about mapping a 2D array to a 1D array for the closed list or something like that. That's a case where we could easily have a reversible hash function. Okay, so those are the hash function properties, and you will be required to know them, but, you know, you remembered all that from, like, grade 10 math class, I'm sure, just like I did. Okay, so let's look over a couple of very simple hash function examples. If anyone has any questions, feel free to type them in the chat. I can answer some of them now. All right, so no questions yet. So, some examples of simple hash functions. Let's look at modulus hashing. So here, we're going to have a hash function h. It's going to take in an integer, and it's going to return an integer. So modulus hashing, all it does is take an integer in a larger range and return a value of an integer in a lesser range. And I'll show an example of why we may want to do this. So for example here, simple modulus hashing is just taking in an input value of x and modding it by some n. So for example, if we have a value of n equal to 10, and we have an input range of x being from 0 to 1,000, then those numbers 0 to 1,000 are going to go into our input range from 0 to 10 because we're modulusing it. So if you remember what modulus is, it's actually the remainder operator. So we take the input value, divide it by this, and gives us a value of n. And as someone in the chat just said, yes, that splits the input value into n different buckets. And so I can show you this with my pen here. And so what the modulus operator does, if we have, let's say we have 3, 4, 5, 6, 7, 8. So here, our number n would be equal to 8. So our input values might be between 0 and 1,000. And when we modulus, essentially what we're doing is we're taking our input value of x, we're dividing it by 8 and then getting the remainder. Okay? So our values would be going into one of these buckets here. So we have an output range, or an input range, sorry, that is larger than our output range, and we use the modulus operator to bucket these values. And so this acts as a sort of truncation, right? It only cares about the lower order bits in the number. So be careful of uniformity if x is not a multiple of n. So what that means, for example, let me go back over to the blackboard here. So what do I mean by uniformity in this case? Let me just show you here. So I'll just leave that on the board. So let's say we have a hash function and we have an output range of 0 to 8, right? So 0, 1, all the way up to 8. Now let's take our input range as values from 0 to 16. So the input range maps as a multiple of the output range. So the values of 0 to 16, well, 0 would be here, then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Well, I guess 0 to 15, right? Okay, so our input size is a multiple of the output range. So what we can see is if we hashed every possible value in the input range, then we'd get 2 values in each of the output range buckets. But if I did something like hashing 0 to 10, then what we'd see is I'd get 1, 2, 3, 4, 5, 6, 7, 8, then 9 and 10, right? And so these two output values would have more input values that created them as opposed to the last ones, right? And so that's not great for uniformity, but it's actually the best case we could do here. But just be careful of uniformity when you do this sort of thing. Okay, back to the PowerPoint. And so this modulus hash function is often used in a hash lookup or a hash table. We may have some complex hash function that takes like a string of data or something like that and turns it into a larger integer. And then what we can do in order to look up the place for that larger integer in our hash table is just use the modulus operator with the size of the hash table. Also, what we can do is something called binning. So where this one was, say, putting one value here, then one value here, we can have sort of the opposite of that where we have binning. And so let's take the same input range of 1 to 1,000 and put this into, again, somewhere values from 0 to 10. And what this is going to do is instead of using the modulus operator, we're going to use the dividing operator, all right? So the difference would be, let me go back to the blackboard again. Whereas before, we would have like 1, 2, 3, 4, etc., with the binning operator. If we had, say, 1 to 1,000 as our input into 8, then actually 1 to 8 would all map here. Oh my god, that's really, really small. Let me change the font size of that. So 1 to 8 would each map here, right? Because we're dividing by 8. Then 9 to 15, or 9 to 16 would each go here. Sorry, this is actually 0 to 7 would each go here. Then 8 to 15 would map here, right? Because 0 to 7 divided by 8 would be 0, so it would go in the 0 index. 8 to 15 divided by 8 would be 1. It would go in the 1 index. Then 9 to 23... No, sorry, geez. 16 to 23 would go in here, etc., etc. So instead of going 1, 2, 3, 4, 5, 6, 7 across, it would go 1, 2, 3, 4, 5, 6, 7 in this bin, 8, 9, 10, 11, 12, 13, 14, 15 in this bin, etc. So that's the way that those hash functions operate. And if we're doing something like we want to hash functions in a row starting at 0, then this may not have the best uniformity properties for us. But overall, it might have the same as hashing. So we can almost look at this as sort of the opposite of the modulus operator, right? So the modulus spread them out one by one, but this one does binning where some will go in the first one, some will go in the second one, etc. But that's all really easy because that's just integer hashing. Let's look at a little more complicated hashing, still kind of easy, string hashing. So let's consider my name, right? Let's hash my name into a value. One possible way, probably the easiest possible way to hash a string is let's just sum up the characters in the string. So we'll look up the ASCII character values in the ASCII character table of Churchill. And so over here, I can see this, right? So the value of C is 67, the value of H is 104, the value of U is 117, the value of R is 114, blah, blah, blah. And when we add them up, we get 926. Okay, so now it's going to be quiz time, all right? Is the summation of character values in a string, tell me whether or not it's injective or surjective or neither or both in the chat. So is it injective and is it surjective? Tell me yes or no to injective and yes or no to surjective. So remember, it's not either or. There's a value for both, right? Something can be both injective or surjective or neither. So you have to tell me whether or not it's injective and whether or not it's surjective. So everyone is saying that it's surjective. Everybody. Just surjective. Well, let's go back and see. So this function is an example of something that's injective but not surjective, okay? So that means that every x value would have a unique y value. But if we think about it, the string summation, that's not injective, right? And the reason for that is because the string AB and the string BA would produce the same hash value. Because we're just taking each value and we're summing them, right? So it's not injective. But is it surjective? So here's an example of a non-injective but surjective function. And surjective means that the output range, for the output range, there is an input which produces it. And so we can think, yes, for any integer between 1 and whatever you want, as long as we have no real restraint on the length of the input string, then yes, there will be an output value. There will be an input string that produces this value, okay? And so, how is the distribution of this, right? So is it uniformly distributed? What can someone say about the uniformity of this hashing function? This one isn't as easy to answer. Do you think this will... Okay, here's an easier question to answer in the chat. Will this be perfectly uniform? I'm going to open my Blackboard. So someone said no. Can you give me a reason for that? I'm not asking if it's a perfect hash function. I'm asking if it's uniform. Okay, so let's go over to the Blackboard, and let's think about the case where we're just hashing random strings. And let's say our strings are, I don't know, a certain length. Well, what we actually run into in this problem is that if we just choose random integers, okay? So yeah, some people in the chat are talking about the fact that, like, in the English language, there are some strings which have more letters than other strings, or some characters appear more often in English, right? But even without all of that like English language, hey, words can be different stuff, what we will actually find if we take the values of a bunch of strings from random numbers, then we'll actually end up, I think, now you may correct me if I'm wrong, but if I just take random strings, because of the property that we saw before, where I was able to hash, why isn't this working? Okay. Where, you know, I said that like AB hashed to the same value as BA. Similar to that, like ABCD will hash to the same value as BADC and BDCA. And so what I think will actually happen, I haven't actually tested this, but I think you'll actually probably get like a normal distribution over this. So if you have a certain range of input values, right, a lot of them, based on just random character selection, will come right in the middle here. You'll get very, very few strings, which are like all A's, and you'll get very, very few strings, which are like all Z's, and most of them will fall in the middle here somewhere and have like these middle range values. And so I do not think that that is very well distributed. Back to the PowerPoint. There's an easy question. We've already kind of answered this one. Is the character summation hash function reversible? All right, so everyone immediately saying no, and that's obvious, as I said before, because if AB maps to the same X as BA, right, then if we tried to reverse X, we don't know where that would come from. And not only that, but AB would map to the same string as C. So, yeah, this is not uniform whatsoever. Not only that, but the input character order doesn't even matter, right? So if I hash Churchill, that's the same as matching C, C, I, L, L, H, U, Chihulio. Oh God, I can't even spell my own name out of order. It's the same thing as if I had reversed it or mixed up the characters exactly, right? So no, the input character order doesn't matter. And for things like passwords, that will be crazy bad, right? Because if I had let's say my password was pass1 and yours was 1pass or P1ass, then all of these would hash to the same thing. And so someone typing in any of these passwords would be able to log into the system. So what I'm saying is here, do not use character summation as your string hashing function. All right. Another thing that we can do is called block summation. So what we can do in block summation is take blocks of n characters at a time. And so, for example, we could interpret this as a single long integer, and we could sum the resulting integers, right? So for example, if I take chur and chill and L, and I concatenate their ASCII values, then I might get a really long number plus a really long number and then plus this number over here, right? And so here, my hash of Churchill would give me this value. And then let's say I had a dictionary table which maybe had 1,000 values, right? I could map this to one of those 1,000 values by using mod 1,000. Okay, so again, I could apply my same logic to say whether or not this was injective or surjective or reversible, and it turns out that, again, none of those properties hold to this, right? And the character order only matters within the block of words and not the entire words. All right. Here's another example of geometric hashing. So what is extremely common, and you probably won't find anything other than this, is that if we do implement a hash table, we're going to implement the buckets of that table as a one-dimensional array, right? And one-dimensional arrays are really good because of cache coherency. And so everything is together in memory, and so things are really fast to look up. And so, for example, in our assignment, we might have like the closed list. And so for the closed list, we have a two-dimensional array. So let's say this is our grid that we're doing pathfinding on. And let's say we want to store some values related to the grid in our one-dimensional array hash lookup table, but our actual environment is a two-dimensional environment. So what we want to do here is we want to map a 2D array index, so an X and a Y, into a 1D array index. So for example, maybe I want to do something like map this value to this value, or this value to this value, or this value to this value, right? So I want to take values from my input range, which is my 2D array, and produce values in my output range. And so my input is going to be the XY, and my output is going to be the index into a 1D array. Let's look at one possible hash function. And so the hash function on f of xy is going to be y times width plus x. All right, so let's have a look at that over on the blackboard. Let me just erase what I had here before. Okay, so we go over to the blackboard, and now let's erase. Oh my God, let's select some of this and erase this, and select some of this and erase this. Here's my behind-the-scenes blackboard. Oh my God. Well, what are you gonna do? Let's go here, and we have our 2D array down here. Let's draw some lines. How's everyone else doing today? I'm going to be drawing lines for a minute here. Okay, so there's my columns. Now I'm making the rows. Okay. So, what is my width here? My width is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11. And my height is 1, 2, 3, 4, 5, 6. You know what? I don't like 11. Yes, let's use 10. That's a much easier value to do mental math with. So, let's go back here and we will... Oh no, I ran into that problem before. I'm not going to be bamboozled again. Let's do this. There we go. So my input, my width, oh my God, color, width equals 10, height equals 6. All right. Now, what was my hash function? It was f of xy equals y times width plus height. Alrighty. So I've just learned that I probably shouldn't be asking how people are doing in the chat. Okay, so over here, my one-dimensional array is going to have 66 possible output values, right? So I have 66 possible input values, and I'm going to have a 1D array with 66 possible output values. Okay. Now let's apply our function. So down here, I have, let's just go through a few of these values and produce outputs. So here I have 0, 0, right? So if I apply my function, it's 0 times 10 plus 0. So that is going to be 0. So this maps to here. Here I have 0 in the x and 1 in the y. So I have y times width plus height. Is this how I want to be showing it? Y times width plus height. No, I'm going to go downwards. Okay, I'm going to iterate this way. So, wait. Not plus height, plus x. I'm an idiot. Sorry about that. This is what happens when you do it live. Why didn't someone correct me? All right. Y times width plus x. Okay. So, Oh, yeah, you're right. Ah, Jesus. Okay. So here, this is 1, 0. Thank you in the chat for correcting me. I was doing 0, 1. That's why it wasn't working out. So let's hash this one now, the 1, 0. So it's y, which is 0, times width, which is 0, plus x. So this one maps here. Okay? Similarly, this is 2, 0. So this is going to map to y, which is 0 times width plus x. So this is 2. And then this one's going to map to 3, to 4, to 5, to 6, to 7, to 8, to 9. And now what's going to happen is when we come down here, which is 0, 1, and then, yeah, it was 66 because I had 11 initially. Sorry. So there's 60 values. You're right. So now I have value 0, 1. So this is where it starts to get interesting. So we had a width equal to 10. So it's y times width. So 1 times 10 plus x, which is 0. So now we go into 10. And then we'll have 11, 12, 13, etc. Right? So this is mapping the input range, which is the x, y values of the indices of this two-dimensional array. And this is going to be a minimal perfect hash function into our one-dimensional array. So every value of the input range has a unique value in the output range. And it's also reversible. Okay? So if I go back to the slides here, to the PowerPoint, if I take the values of the indices of the array and apply this formula to it, then I can get back to the y value by taking I divided by the width, and I can get back to the x value by taking I modulus the width. And so this being a perfect hash, a minimal perfect hash function, it's also reversible. And so for our A star assignment, if we want to, we could use a 1D Boolean array as the closed list by applying this hashing function. And so the 1D array would be our hash table, and we just talked about the hash function, which would get us from our 2D array down to our 1D array. Okay. So far, everything has been nice and fine and dandy and magical, and we haven't run into a hash collision yet. Hash collisions suck, right? If we didn't have hash collisions, the world would be a wonderful place. So, hashing data into an integer is typically used to index in a hash table or an array, as we just saw. So if we have an array of size n, then the hash function typically finishes with a modulus n operator, meaning that we somehow have to get our inputs of a huge possible size into this integer of size n. And so a hash collision occurs when two of those inputs produce the same output hash value, causing a collision inside the hash table. Let's look at an example of this, okay? So over here, again, we have this example of John Smith and Sandra D. Whatever hash function happened to be used here, let's say we have this is our one-dimensional array with size 16. Whatever hash function we used produced the same output value for the index of the lookup into our hash table. And so this is a hash collision. So for example, if we had stored like John Smith's phone number in this address book hash table, and then we want to store Sandra D's, well, it's producing the same index. So what are we going to do? Also down here is an example. I got to move my camera because this is actually an interesting example. So down here in the bottom right, we see an example of the CRC32 hash function, which is actually like, a hash function that was used for things. And so we have hash values which are mapped into 32-bit values. Okay, so each of these is a hexadecimal value, which is 4 bits. And so you take a string and you map it to a 32-bit value. That's why it's CRC32. So for example, spaceship becomes this value, banana becomes this value, but it turned out that if you had plumless and you hashed it, and buckaroo and hashed it, the input values of plumless and buckaroo produce the same output value. So if your hashing scheme for the passwords for your website was just CRC32, then someone who had the password plumless, you'd be able to log into that website using Buckaroo. Now that doesn't take into account like salting and all that kind of security stuff, but we're not really worried about that for this course. All right. So if two values collide, how do we store their values in the hash table? Well, it turns out that there are solutions, but they're all going to be a little bit expensive. But first, before we talk about the solutions, let's actually talk about, let me move this up here because this is going to happen a few times. What is the probability of a collision actually occurring? Okay, we need to know what that probability is. And it may not actually be intuitive. So let's talk about this birthday problem. What is the probability that with n people in the class, that two people have the same birthday? Okay? It turns out that you may think, well, it turns out, counterintuitively, with 365 days in the year, you actually have a 50% probability of two people having the same birthday in a class of only 23 people. That's crazy, right? Like, why is it only 23 birthday? Why is it only 23 people? Well, I'll show you why back at the blackboard. Oh my God, there's so much stuff on the blackboard. Let me erase the blackboard before I go back this time. Oh God. I am not telling you to put your birthdays there. You are doing that of your own willpower. Okay. Let's go back to the blackboard. Yeah. It's like, what is your programmer nickname? It's your birthday followed by your social security number followed by the last 4 digits of your credit card. Post it on Twitter. So, here, let's talk about hash collisions, and we're going to talk about birthday hash collisions, okay? So this is our array for birthday values. Okay, so this is 365 values. Now let's say we have student number 1. And we have student number 1's birthday is going to go right here. So we can talk about the birthday paradox in terms of hashing collisions, which is pretty cool. So the probability of one person having the same birthday as someone else is 0, obviously. But now comes along the second person. And so there is one birthday here on, let's say, January 5th or whatever it is. So the probability that the second person has the same birthday as someone else is 1 in 365, right? Because there's only one other value here. So let's say the second person has this birthday on this day. Now we look at the third person. Well, the third person now has a 2 in 365 chance. And what's that? Like 182-ish? 182.5? So, just by adding one more person, your chances of having the same birthday as someone else double just with the same person. Now, the third person might have the birthday here. The fourth person might have the birthday here. But now, the fifth person has a 1 in, what, like 45 chance of having the same birthday? 365, oh no, 90-something. 90 whatever, 91 point something. So the fifth person now has a 4 in 365 chance of having the same birthday as someone else. And it turns out that, the probability of two people having the same birthday is all of these probabilities multiplied together. And it turns out that at around 200 or at around 23 people, that's where you reach a 50% probability. So if we go back to the PowerPoint, oh my God. With each new hash, the probability of hitting a previous hash value rises. So it's not like the probability stays the same. As you fill up the hash table, the probability of a hash collision goes up and up and up, okay? So you have a 50% probability of a hash collision at approximately the square root of the output range, okay? So if you look at 23, 23 is approximately the square root of 365. And this is a good heuristic. It's not exact, but it's a good heuristic. So if we have a 32-bit range, so even if we have, so 32 bits is what, 4 billion? Something like that? Can someone look that up for me? It's 4.2 billion or something like that. So if we have, even if we say, okay, I'm going to use all my RAM, I'm going to use 4 gigs of RAM for my hash table, I'm going to have 32 or 4 billion possible values in my hash table. If we have a hash function that produces randomized, or not random, but like outputs that are evenly distributed, then we have a 50% probability of a hash collision after only 70,000 entries into an array size of 4 billion. And after only 250,000, we have a 99% chance of a hash collision occurring. So, you cannot solve the hash collision problem by making your hash table bigger, because you have to square the size of the hash table in order to reduce the probability of hash tables occurring or hash collisions occurring. Okay? So down here, there's just a few graphs of what this looks like. All right. So again, a hash table, which we've talked about informally, is also called a hash map or a lookup table, etc. So yeah, someone posted almost 4.3 billion as a 32-bit integer. It's a data structure that associates some data with values via a key or identifier. So if we have a hash function on our data, this produces a key, and then what we do, is the hash value is indexed by that key somehow, and we're going to store the data in there. So this can be implemented in many, many ways, but the most common way and the most efficient way is to use an array. So for example, Python built-in dictionaries use hash tables. Perhaps JavaScript does too. I'm not exactly sure though. So hash tables can serve as this is one possible use as a hash table. I want to talk a little bit about memoization. So a hash table can be used as a cache to store relatively expensive computations. And so if we do this process is called memoization. So it's like taking a memo. So hash tables enable programs to use additional memory to gain speed. And ideally, hash table query time is independent of the number of entries. So here, for example, if you use Python, this is a really interesting thing called memoization. It's a Python implementation of memoization. And so what happens is, essentially, without going through each line of code, when I call this function, it's going to first look up in a hash table, hey, have I called this function before with this particular input? If I have, then just look up the value in the hash table. If I haven't, then compute the value. And so this is actually used a lot of the time in heuristic search, especially in alpha, beta, and minimax search, which we'll look at later, as a way to save on computation time. So let's say, for example, if our hash function in assignment 2 was really expensive. Let's say it took like many milliseconds to compute our heuristic function in assignment 2. Then what we could do is we could use a hash table to store the results of computing our heuristic function, and later, if we wanted to compute the heuristic function for the exact same state, then we could just look it up in the hash table, right? Now, in assignment 2, you are not allowed to do that. Do not do any memoization in assignment 2. But this is just a possibility that you could do if you wanted to. All right. So, our hash table implementation, we're going to implement the hash table as a one-dimensional array. We want to use contiguous memory. This is important for caching, and I'll tell you why in a second. Each array index is a bucket in our array, and our job is to put things into buckets. We are bucket putter inners, okay? So, For example, if we had a phone book use case for our hash table, our keys then would be our names that we're trying to store phone numbers for, and our hash table would produce whatever the hash function is. The hash function would produce the index to look up the value in our hash table that we would be storing. Okay? So for example here, Lisa Smith would go up here, John Smith would go down here, Sandra D would go down here. So what values do we... Oh, let me... No, I'll talk about that later. What values do we actually want to store inside our hash tables, right? That this may be a decision you have to make when creating your hash table. So for example, over here, we store, or we have as an input values, we have the names, and we want to store our phone numbers, which is the data that we want to store. Oftentimes, we may also want to store the original input as a key value pair. So for example, here in our phone book, at the index produced by our hash function, we also store the name. And whether or not we want to store the original input name or not store the original input name, this entirely depends on our application, right? And it'll turn out that when we want to do certain types of hash collision resolution, so like what do we do when there's a hash collision, we may actually need these values to be stored as well. So again, just recall our hash function properties. The reason these hash functions are occurring is when we have non-injective functions, right? So typically, even if our hash function is really good, the input range size is going to be bigger than our output range size, right? So just think about it. The possible range of input names of possible strings is way bigger than our possible number of entries in our hash table. That's just always going to be the case. So no matter how smart our hash function is, we're always going to have this exact case where we have more things to hash than we do have possible output hash values. And so this is why hash collisions are always going to occur for interesting scenarios. And interesting meaning not trivial, like perfect hash functions. So when we talk about hash collisions, we also want to talk about like the hash table load factor. So the load factor is a value which is n over k, and this is a good exam question as well. So n is the number of entries in the table, and k is the total number of buckets, okay? So what this means is if we've put n things into k buckets, then the load factor is n over k. And typically n is going to be bigger than k. So typically performance of a hash table decreases with increasing load factor due to hash collisions. So what are hash collisions? So if we had a bijective hash function with the table size equal to the input size, then we would have no hash collisions, right? We are lucky in assignment 2 that if we have a 2D array that we want to translate into a 1D array, then that can happen no problem. But in practice, our input range is usually way bigger than our table size. So a hash collision is going to occur when the bucket for a new table entry is already occupied. And so we've already seen this, right? So a hash collision occurs when the hash of one input is equal to the hash of another input. So down here, we've computed John Smith's hash function and stored it. But what happens when we compute Sandra D? Like, what do we want to do? We have the same hash value. What can we possibly do here? So it's extremely important to have a good hash collision resolution strategy. And the strategy for hash table resolution is what separates a lot of hash table implementations. And the hashing part is usually pretty easy, right? It's the resolution part that is the most complicated. So the simplest thing we could possibly do is just overwrite the value, right? So for example, if the bucket is already occupied by John's phone number, if we have Sandra who produces the same index, when we just store Sandra's number. And the downside of this, however, is that John's number gets overwritten, right? So you can see why this may be an issue. So we may have conditions for overwriting. So for example, maybe we want to store the newest value. Or if it's a phone book, for example, maybe we're at a business and our oldest customers are more important or something like that, and so we would want to keep John's number and say, well, sorry, Sandra, John has a place in the phone book. Maybe we'd want to store the minimum or maximum value. So say there was some computation and big values meant something good. Well, we want to hold on to that big value. Or maybe if we were doing some sort of heuristic search and we stored it in a hash table, we'd want to store the deepest search result, something like that. But with overwriting, in practice, too much data is lost, and so we don't want to do this. One thing that is used is something called chaining. All right. So this lecture is going to go about 10 or 15 minutes overtime, but whatever. That's the beauty of the VODs. In chaining, each bucket in the hash table, so again, these are our hash table buckets. Over here, these are our hash table buckets, right? And these are our hash table indices. Except instead of each bucket just containing one value now, each bucket actually contains a list of values. And so instead of just putting something into the hash table, whenever we insert into a bucket, we just add it to the end of a list. And if the hash function is uniform, then each list will be small and efficient, right? If we're putting each value, If we're putting each value uniformly in here, then each of these lists should be pretty small, and they should be around the same size. However, in the worst possible case, let's say we had, like our hash function just always returned 0, or something stupid like that. We would just have one huge list, right? And in that case, we would have like O of n query time, and that's really, really bad. So the average query time is going to be the average list size. And if we have a uniform hash function, then the average query time is going to be approximately equal to the load factor, right? The load factor is going to tell us the average size of a list in our chaining application. And of course, we could replace a list with a set or a vector or whatever. It doesn't matter how we're storing them, but we're just going to use a list because it's easy to visualize. And if you use chaining for your hash collision resolution, then your hash table could grow beyond the initial array size, right? So I could have an array of size 10 that had 1 million things in it because each of my buckets has a list in it. So just be aware of that. So here's what you may have when you use chaining. So bucket 0 could have one item in it, bucket 2 could have another item in it. So here we use literally just a linked list in each of our hash table buckets, okay? So chaining is one possible strategy. And in chaining, what we would have to do in order to go look up the value, let's say now if this is the state of my list and I want to look up Sandra D's phone number, then this is why I would also have to store Sandra D's name here, right? So I'm going to hash Sandra D. I'm going to put it at the end of the list, so now I have this entry. When I go to look up Sandra D, I hash the value, I look up the bucket in the hash table, and then I have to look through the list for a matching name, and once I find the matching name, then I look up the phone number, okay? So that's how you would actually do the query in a chaining application. Another possible hash collision resolution is called open addressing. In open addressing, all records are actually stored inside the array, so we no longer have these chaining structures. We have no lists or external data structures. And here's what happens. When a new entry is to be inserted into the array, if there's no collision, we just put it there into that index. If there is a collision, however, we scan forward into the array somehow to find another open space into the array. When we find another open space with our look forward function, then we will insert it into the first open space that we find. And then we also, just like chaining, we have to have a secondary key that's required for lookup. So when we look up an entry, what we do is we look at the original index. If the second hash value matches, then we return the value. If we scan for, otherwise, if it's not If the second hash value doesn't match, then we scan forward with our given scanning strategy until we find the second value. So, here's an example of open addressing with linear probing insert. So what we do here is whenever we have a hash function, a hash collision, right? So I've got John Smith and Sandra D here. Let's say that John Smith and Sandra D. So John Smith was in there. When we go to insert Sandra D, if it was empty, then we would have put it here. But John Smith was there, so we couldn't insert it. So what we did was we just went ahead linearly and we just scanned one forward until we found a place to put it. And that happened to be in place 153. And then later on, the same thing happened, but with Ted Baker. So when we hashed Ted Baker, we got 153, but oh look, Sandra's here again, causing problems. And so we would scan forward to 154 and then be able to put Ted Baker in there. And so, again, we look at the next bucket. If it's empty, we insert it. If it's blocked, go to the next one. When we're inserting, we need this secondary key value or we can't do lookup. Because if we couldn't tell, if we didn't have a second hash value or we didn't have the person's name, we couldn't actually tell whether or not when we looked up the name, whether this was the right name. So when we look up, we look at the hash index, right? So let's say now we are going to look up Ted Baker's phone number. So we look at the hash index. Okay, we're at 153, so we're right here. If the second key matches, then I return. So does Ted Baker match Sandra D? No, so we can't return. If no match, then we go to the next one. So does Ted Baker match Ted Baker? Yes, so I return that value. And we keep repeating until the second key is matched. Now, linear probing can suffer from clustering, okay? So if we have a hash collision and we do linear probing, then we're going to store the hash collisioned value in the next index. And that's not very good. That's creating clusters around hash collisions. And that's actually the worst possible case. So linear probing can suffer from clustering. And what we end up getting is a few very dense clustering of values resulting in slow lookup times. So there's other possible values as well. So for example, we could have quadratic probing. So we could have add a quadratic to the index. And so as we scan forward, we'd jump more and more. We could have double hashing. So instead of just moving forward by one or quadratic, we could actually hash the value a second time and then move forward in the array by that hash value. And all these different strategies, and there's many more of them, help spread out entries in order to avoid clusters in our hash table. All right, there's one last one that I'll talk about, and this is called coalesced hashing. So it's going to combine the ideas of chaining and open addressing. So the chain structure is used on a collision, but the chain is going to point to buckets in the table. And what we have here is better memory performance. So for example, here, we kind of use the same thing as open addressing, where we're going to store the next value in the table, right? We look forward in the table for an open value, but then what we do is we create a pointer to that location in the table. And so we have a chain that we can follow for more efficient lookups, and we have better memory performance, but now we lose one of the benefits of chaining resolution, whereas now we can only store the number of entries that we have in our table. And many, many other strategies exist, but we're not going to talk about those right now. Okay, so game state hashing. We're talking about games in this course, right? And we're talking about states. And so we often might want to store some relevant information about game states. So for example, we may want to store the policy. So if we're in this state, what sort of move do we want to make? Or maybe we want to store the value or a heuristic, like how good a state is. And we can store this using a hash table, right? And some of these hash tables are super trivial, where states are really simple. So for example, here in assignment 2, as I saw before, I could have a big 1D array, and I could hash all of these values, like this state into this one into this one, and the 1D array would just have to be of the size width by height, and I'm done, right? So that's a really, really easy example. Similarly, if we're talking about like a blackjack betting table, then I can also store this trivially in an array. Okay. So this is just examples of trivial hash functions. But what about non-trivial state hashing? What do we do here? So for games with non-tabular structures, how do we compute the index for a state? So one way to do this is to come up with a custom function for each separate game, right? So I'm going to have a function which like takes Mario's position and multiplies it by 748 and the Goomba's position and multiplies it by, and that's just nonsense, right? That can be really time consuming if we have to write a new hash function for every possible game or every possible state of the game. And it also may be very expensive to compute. So what I'm going to show you here is one possible hash function which I've used and had great success with it. It's called the Zobrist hash function. And the Zobrist hash function is often used in games, and it's going to take games with really complex states. Okay, so for example, how in the hell would you write a hash function for a chessboard state? Right? Because here's the board, and yes, it looks like it has a tabular structure, but what we actually have to store is there is a black rook on space A8, and there is a white pawn on space A2, and there's so many possible configurations of this. How would we have a hash function to compute that? Not only that, but how would we have a hash function that's really easy to compute and requires little computation time? So the Zobrist hash function is going to ensure uniformity. It's going to be very fast to compute because it's actually going to be incremental. So if we start the board with a given hash value, the given Zobrist hash value, we can actually update the hash value when we do a move by doing a single operation. And we can also reverse action hash values to make that undo very fast as well. And so the Zobrist hash function is going to rely on two main components. It's going to rely on a table of random values that we'll show later. And these random values, they're random, but they're the same every time you call the Zobrist function, okay? They're random in so that they're secure cryptographically, not random as in every time we call the Zobrist hash function, we're going to get a random value. And we're also going to rely on the Xor operator. And what is the Xor operator? The Xor operator it's the best operator, okay? I will say that Xor is objectively the best operator. Now you say, how can something be the best operator? I love the Xor operator. It's used for so many different things. The Xor operator is denoted by the caret or the hat here, right? So if I take two values, say two integers, and I XOR them, the result of the XOR is the bitwise XOR of each bit in the number, okay? So XOR's lookup table basically says if the two input values are the same, the output is 0. If the two inputs are different, then it's a 1. So its XOR actually stands for exclusive OR, okay? So are they exclusively different? Then it's a 1. If they're not, then it's a 0. So here's an example where I have a number A, a number B, and a number C. So I'm going to do the bitwise XOR of each of them. So 1 is the same as 1, so this is a 0 in the output. 0 is the same as 0, this is a 0. All these are the same. These are different, and so this is a 1 in the output. These are different, so it's a 1 in the output. So A with this value, XOR B with this value is equal to C with this value, okay? So it's just the exclusive ORing of each bit. We have another interesting property here, which is really cool, is if we take A and we XOR it with 0, what we get out is A. Because a 1 XORed with 0 is a 1, and a 0 XORed with 0 is a 0. See how that works? So if we take any value and XOR it with all zeros, we get that value back, and that'll help us in the future. Not only that, but from this, we can see that XOR is actually reversible. So if we take any value and we XOR it with itself, we get out 0. Okay? So XOR is transitive and XOR is reversible. It's a really cool operator. So we have, up here, we have an example where A XOR B is equal to this C value. A XOR A is equal to itself. A XOR 0 is equal to A. And we can look at things like this. So what is the result of A XOR A XOR B? Well, if A XOR A is equal to 0, and 0 XOR anything is equal to itself, then this becomes a 0. So that would be 0 XOR B, and we get B. Okay. And if we have A XOR B equal to C, then we have C XOR A equal to B, and C XOR B equal to A. The XOR operator is reversible. This is very, very important. And so we're going to use this in our Zobrist hash function, and this is used in many, many other hash functions as well. Okay, so in our Zobrist hash function, let's take the example of chess. How are we going to compute our hash function for that? Well, let's take our initial state hash where there's absolutely nothing on the chessboard, and we'll start out at zeros. And what we're going to do is we're going to generate a random integer for each of our board positions. And also, for each position, we're going to have a random integer for each piece. And what that means is that this is how this is going to happen. On our chessboard, okay, we're going to have some values here, and I'm drawing a smaller chessboard just so it's easier. In here, I'm going to compute random values, so like whatever, like, oh geez, I just drew a random value up there. Maybe it's like X for a B or something. And I'm going to store them in this table. So here, for each position, I'm going to have a random integer for each piece. So for example, here for pawn, this might be my random value. For a black rook, it might be another random value. For a white knight, it might be another random value. Okay, so for each piece on the board, I'm going to have a random value which is unique to every possible piece that could be there. Now, for a random table, this is going to end up with a size of 64 by 12 because there's 12 possible pieces on the board, right? And so my random table of values is going to be indexed by the position of the board. There's 64 of those, and there's 12 possible pieces. And what this random value is going to represent is that this piece is at this position on the board, okay? So if I look up, for example, R indexed by this position, and the second index is the white pawn, then that is the random value for a white pawn being on that place on the board. Now, we can hash an action of putting a piece on the board in the following way. So if we take our current hash function and we want to put a piece on the board, then what I can do is take the hash function and XOR it with the random value associated with putting a piece on the board at that spot. And I can also remove a piece from the board by doing the exact same thing. So here, for example, if let me do this on the blackboard, actually. So I'll erase what I have on the blackboard right now. Let me just go back. I'm clearing the blackboard. We go over to the blackboard. And so we're going to have our chessboard like this, right? So we've got some pieces here. Okay, so now let's go walk through one very simple example. So let's say we have here a value at like A1 and we have like B4, for example. So let's say our random value, so R of A1 for having a black queen is equal to 01101010. Okay? And the random value for having a, at B4, for having a white king is equal to 11110010. Okay? So, we're going to start out with our hash value. Why did I put two things there for H? Is initially going to equal 00000000. Now, let's put that black queen here on this piece. So what we do is we look up in our table what is the hash value for having a black queen at A1. And so we're going to XOR 0110 1010. What we get out of that is 0 1 0 1 0 1 1 0, right? And so, well, that was easy because anything XOR 0 is itself. And now what we want to do is we want to put the white king on space B4. So what we do is we take the current hash value and we XOR it with the value of having a white king at space B4. So that is 1111 0010. So we do the XOR of this, we get 1001 1000. Okay, so now let's say that we want to remove the queen from the board, right? So in order to put a piece on the board or remove a piece from the board, what we do, oh my god, my erasing is white. So I'm going to take the black queen off of the board. And in order to do that, I do the same thing as when I put the piece on the board, is I'm going to XOR it with its random value. So this is the random value for taking the piece off of here, right? So it's 0110 1010. So if I do this, I'll get 111. Sorry, what was the value here? I may have made a mistake. So when I copied this down, this is 1, this is 1, this is 0, this is 1, this is 1, this is 0, 0, 0. So I want to XOR this. 1 and 0 becomes a 1. 0 and 1 becomes a 1. 0 and 1 becomes a 1. Oh, 1 and 0 becomes a 1. I just had them misaligned here. Sorry about that. 1 and 1 becomes a 0. 0 and 0 becomes a 0. 0 and 0 becomes a 1, and 0 and 0 becomes a 0. And look what I have. I have the exact value for having a king on the board at B4. Right? So now if, for example, if I put a black pawn or a couple of black pawns down here, oh, sorry, you can't see the value of that. I don't exactly know how to fix that. Here we go. I'll just do this as a temporary fix for now, which is after I put the piece, so I put the black queen on the board by XORing it with its value. I put the white king on the board by XORing it with its value. I got a new hash function. And then in order to take the black queen off the board, all I did was XOR it with its value. And then what I got in the end was this value. And if I check up here, that actually matches with the hash value associated with having just a king on B4. And so move by move, I can increment or I can update my hash value and get these values really, really quickly, okay? And so that's how you do the Zobrist hashing. Oh, was that the issue? What was the issue with this? I don't know. I'll fix that later. But that's how we do Zobrist hashing. And that may come into assignment 3 for the grad students. Alrighty. So back to the slides. I have one quick more thing to show you, which is really cool. Alright. So, let's talk about data recovery. XOR is such a cool function. And this is going to blow my mind. This blew my mind the first time I saw it. Oh, excuse me. this blew my mind the first time I saw it, and hopefully it blows your mind as well. Let's talk about like hard drive data recovery. So if you have data stored in like a RAID array is a bunch of hard drives that are tied together to form sort of one big hard drive. You can get RAID arrays that have something called disk redundancy, okay? So let's say I have 4 disks and I want to join them together in a RAID. And what I want to be able to do is add another disk, and so that by adding another disk, I can make it so that if any of the disks in my system fail, I don't lose any of my data. So how do RAID arrays do that? So for example, if I have 4 disks worth of data, and I add a 5th disk to the array, I can make it so that if any of those 5 disks fail, I still have all of my data. So let's illustrate how Xor can do that for us. Here's my first disk's values, okay? So I'm going to take all the bits on the hard drive and just list them vertically here for ease of illustration. So my bits on this hard drive are 10, 10, 10, 101. For disk 2, I have these bits. For disk 3, I have these bits. And for disk 4, I have these bits. Now what I'm going to do is I'm going to introduce a new hard drive to this array, and this is going to be my Xor disk. And what I'm going to do, each bit on this disk is going to get the value of XORing all of these bits together. Okay? So what I get now when I do that is this. Okay, so these are the XOR bits. So 1 XOR 0, XOR 1, XOR 0 is 0. 0, 1, 1, 1 is 1. So we XOR all these together. This is what we get. Now, let's say that disk 2 dies. Uh-oh, I lost my data on disk 2. Or did you? Right? What we said before is that Xor is reversible. So if one of your disks dies, get a new disk, put it into your array, and do Xor with the 4 other values. And if we do that, what we get back is the original data. So if we remove our Xor disk and we look back at what we did, right? This is the original data we started with, and this is the data that we get if we Xor the bits from all the disks, including the Xor disk. And so this is how, now this is not exactly how like modern RAID systems work. Trust me, they have much more advanced data structures that don't have to do everything in linear time. But this is how you can do data recovery by just using Xor. And it's absolutely incredible. I really like that example because it shows the power of Xor and how its reversibility can be used for a real world application. Okie dokie. So this has gone on for the lecture has gone on a little bit long. And so if you're completely fine with that, you can leave it there. But what I wanted to do real quick is just spend like 10 or 15 minutes, if that, going over a couple of things that I didn't mention for assignment number 2. Okay. So again, assignment 2 is the A-star pathfinding algorithm, which we went over in great detail in the last lecture. But I wanted to just mention a couple of things because a couple of people had some questions. So one question was that like the input that you get for the actions is determined by the GUI here, okay? So when you click the GUI, when you click the interface, it will set the legal actions up here. And that will be passed into the this.config.actions inside your search student class. So if you are not using, like you have to be iterating through this.config.actions. You can't hard code the actions for this assignment like you could for the last one, because if I check here, if I click 4-directional movement, yours has to switch to 4-directional movement. And if you're hard coding the actions, it won't update the values from the GUI, and so that is important. So we'll be checking that as well. Also, I wanted to go over the marking scheme really quick. So this is the assignment 2 marking scheme. So again, we have code style, modularity, and readability, which we have from the previous assignment. So we're not going to be too harsh on that. We have 5% of the assignment for other functionality. So start search properly sets up a new search. So everything that should be there in the start search function, such as the setting of the open and the close lists, are there in that function. The isLegalAction is going to properly compute the legal actions for 4-directional and 8-directional movement, and it doesn't jump over tiles, right, when it does diagonal moves. The A-star pathfinding output is going to be the majority of the marks for the assignment. So for this one, all of your tests have to pass. The GUI probably interacts with the algorithm. Your code, again, should take less than 1 second per path. And the visual inspection, so when we go to run your stuff, it should pass the following behavior. And 25 of these 40 marks for the grad students are going to be the bidirectional search. Now, what I did was I split this assignment up so that you should get everything working with size 1 before you go on to working with size 2 and size 3. And the reason for that is that the size 1 working is worth the majority of the marks on this assignment. But for object sizes of 2 and 3, it's the same as the above, but it's less marks, okay? The connectedness for size 1, so all tests path, and I properly hold down the right mouse button, and everything that's connected gets shown. Similarly, for sizes 2 and 3, you can see that connectedness is not the same for objects of size 3, right? So if I, let me just refresh this, and if I select 1 by 1, you can see that this is not the same as this, right? And it's not the same as this. Oh, sorry, that was student A-star. That's why it wasn't working. So 1 by 1 is not the same as 2 by 2, and is not the same as 3 by 3. Okay, so the connectedness is when you use the solution, it's not the same. But the student A-star was doing something that's not the solution. Okay. So the total assignment mark is out of 100, and the grad students have 25% of their mark devoted to getting the bidirectional search working. Again, so inside the user inside the file here, I have can I? Oh, geez, I want to make this bigger. Okay, this should be fine to read. So I just want to read over this. The code has almost the exact same structure as the first assignment. So for example, we have the start search function. We have a new function is the estimate cost function. This is going to, and it's all explained here for you, is that it's going to return the proper heuristic value, which is a guess at how long we have left to go between a given x and y and the goal x and the goal y. So again, here we have the diagonal Manhattan distance, the cardinal Manhattan distance, and the Pythagorean distance. So you have to implement this function. We have a new function which is canFit, which just returns whether or not an object of a given size can fit at a given xy location. We have isConnected, so this function is going to return whether or not 2 spots on the map are connected. So remember, you should have computed your connected sectors by this point, and the functionality is given in the assignment 2 slides where you have to change this so that this calls your connected sectors. Here we have isLegalAction. That's the same as before, but now you have 8 possible actions. Here's the function where you're going to be computing your sectors, okay? And this is called within the constructor. So the constructor is going to call this .compute sectors, and so you compute the sectors once at the beginning of the object construction. So all of your code has to be inside here. Now, if you want to create a new function, for example, the flood, fill, breadth first search that you have to do for setting the sectors, then you can create a separate function. That's fine, but you just have to do the actual sector computation inside this function. And again, you have your search iteration code. This is going to carry out the A-star search. And then you have your get open and your get closed as well. So depending on how you implement, like if you implement a hash table, like we talked about for your closed list membership lookup, then you're going to have to convert the booleans inside that hash table into a list of XY values for this get closed. Similarly, for the get open, if you end up using this binary heap data structure that I've given you, then you have to actually iterate through the binary heap and return the states here so that the GUI can properly draw the open list. But that's really easy. The binary heap just has like this.content, and you can look through this.content to get those values. Okay, and really easy to add things to the binary heap. You use push. To get the minimum element from the binary heap, you use pop. And when you construct the binary heap, you have to pass in a score function, and I'll let you figure that one out. I'm not going to tell you everything. So this is the assignment code, and it's almost identical to the previous assignment, but I've also, because this assignment is a little bit more complex than the last one, just a little bit, I've given you sort of an order of steps in which I recommend you do the assignment. So first, I recommend construct the function which computes whether a given size agent can fit at a given XY location. So that's going to be used by the compute sectors and isLegal action function. Second, complete the compute sectors algorithm using a 4-directional breadth-first search as shown in the class sides. And then use the results of step 2 to complete the isConnected function, and then test it with the GUI. So the first thing that you should get working in your code is this connectivity, okay? So before you do the A star, get the right-click functionality to work. That's what I recommend. Next, complete the isLegal action function, which will be used by the search iteration. So the isLegal action function that you'll be using by search, if you want to do an optimization, that could actually be calling the connectedness functionality. Then complete the start search function, which is called before the search iteration. Then you want to complete the get open and get closed functions, which will enable you to visually debug your algorithm. Then you complete the search iteration function using A star, okay, with a heuristic of 0. So do not do the heuristics until your A star is actually working. That might seem counterintuitive, but just implement A star and come back here and select the 0 heuristic and see if your A star functionality is working, okay? So A star should work and give you the correct paths, and you should run the tests, and they should all be fine with a heuristic of 0. It's just that when you go to implement the heuristic, your searches will be faster, okay? After that, you want to implement the estimate cost function and then use that with A star. The problem is if you implement the heuristics first, and then you're only testing A star with your heuristics, and you made a mistake in your heuristic calculation, then you could be computing non-optimal paths. But you should be 100% sure that with a heuristic of 0, that your A star is working, okay? So you use a heuristic of 0 when you first test your A star to eliminate the possibility that it was your heuristic that was giving your problems and not the A star function. But it turns out that step 7 is going to be probably the easiest part, because it's just like the last assignment, except instead of just using array.shift or array.pop for breadth first search or depth first search, now what you're doing is you're going through the open list and finding the node with the minimum F value. So what I also recommend is at first, just use an array to store the elements of the open list, and when you want to find the minimum value, just iterate through it and find the minimum cost of G plus H. And then afterwards, once you get that working, then implement it with the binary heap, the binary heap priority queue that we have in order to speed up your search. And then for 6980 students, implement the bidirectional search, okay? And what I also recommend is get all of that working for size 1, and then go on to size 2, because you know your solution works. And it's really, you don't have to duplicate all of this. So if you have code in your assignment that says, if size equal to 1, do this, and if size equal to 2, do this, and if size equal to 3, do this, that is completely wrong. Your functions should handle in the size of the object, okay? And for example, your computed sectors data structure should now be a 3D array like we talked about in the slides, instead of just a 2D array. So don't have a separate variable for the sectors for size 1 and a separate variables for the sector of size 2. So for example here, if you have this dot sectors and you have this equal to like x, y for size 1, then what you could do is just have a 3-dimensional array which is indexed by the size and the x and the y. Okay, so that's how I want you to do it. I don't want you to have sectors or different variables for each size. They should all be just an extra dimension on top of your arrays. All right, so that's all I wanted to mention because I forgot to mention that last time. Thank you so much. I know this was almost a 2-hour lecture, but I just, I didn't have to come back here and talk about this with respect to the assignment, but I wanted to really make sure that all of that was not confusing. So thanks again for tuning in, and I will see you on Tuesday.